So let's try to understand what redox is. Redox is basically a play on word. We have two different words, reduction and oxidation. So there's reduction, there's oxidation, two different processes which we combine as redox. Okay, so you can see that this is a portmanteau of these two words. So how does this work? What is reduction? What is oxidation? So oxidation is if you take the electrons away from something. So electrons transferring like that is oxidation. So you take electron away, that is oxidation. You bring electron to something, that is reduction. You remember that metals prefer to do this, right? So metals prefer to lose electrons. So we can say that metal is something that wants to oxidize. And electrons are usually gained by non-metals. So we can say that non-metal is something that prefers to be reduced, right? So that's their preference. We can also make them gain electrons as far as metals are concerned. We can push the electrons back on them. And that idea comes from the rate of reaction or the preference of reaction or reactivity series, which we talked about, that things that are less reactive, it's easier to give electrons to them. And things that are more reactive as far as metals are concerned, it is difficult to give them electrons. So we talked about it. Reactivity series, for example, sodium is easy to lose electrons for sodium compared to copper. But it's easy to gain electrons for copper compared to sodium because sodium loses faster, gains slower. So that is the idea that we can say that sodium is better at oxidizing compared to copper, and copper is better at reducing compared to sodium. So things that are more, so metals overall, they try to be oxidized. They prefer to be oxidized. They lose electrons. And if you're trying to reduce them, which means if you're trying to give them electrons back, more reactive metal will take longer than the less reactive metal. And that is something, or take more energy to do that. And that is something that we will talk about when we talk about electrolysis. So that's the idea of redox in terms of electrons. You take electrons away, that is oxidation. Losing electrons is oxidation. And that is a metallic character, like metals prefer to do that. And gaining electrons is non-metallic character, and that is called reduction. Now, in terms of hydrogen, it's also the same. You take the hydrogen away, and that is oxidation, and you accept the hydrogen. And I'm not talking about hydrogen ion, I'm talking about hydrogen atom. So you take the hydrogen away, that is oxidation. You give the hydrogen to something, and that is reduction. This is definition that is usually not talked about in O-levels chemistry or IGCSE chemistry. So even if you don't remember the hydrogen, that's perfectly fine. It won't hurt you. Similarly, if you give oxygen to something, that means it is being oxidized. So getting oxygen, that is oxidation, and losing oxygen, that is reduction. So things that accept oxygen, we say that they have been oxidized. So for example, carbon, when you burn it, it becomes carbon dioxide. So we say that carbon is oxidized. Or carbon monoxide, CO, if you give it more oxygen, it also becomes carbon dioxide. So it has one oxygen first, and then it takes another one. So we can say that this is carbon dioxide. And that is also carbon monoxide being oxidized. Similarly, we can take carbon dioxide and we take oxygen away from it. In that case, it will be reduced because you have taken oxygen away from it. So getting oxygen is oxidation. Losing oxygen is reduction. And oxygen can be in terms of, you can say, oxygen atoms again, or oxygen molecules reacting with something. So that's also oxidation. So that's the second definition of this. The third definition is the idea of oxidation state. In metals, we can say that this is, or in ionic compounds, we can say that this is related to charge. But in many covalent compounds, we also have the idea of oxidation state. Oxidation state is simply, if something was in ionic reaction, how much would the charge be? So that's a vague way of looking at oxidation state. If something was in an ionic reaction, what would be the charge? So it doesn't have to be an ionic reaction every time. We're just saying that if something had an ionic bond, what would be the charge? And that is what oxidation state is. So if you give something a higher oxidation state, we say that this is oxidation. And if you take oxidation state, you reduce it, we say that that is reduction. So 4 ways of looking at oxidation state. You can loosely call it charge, that it's not actually charge. Like oxidation state is a bigger term or an umbrella term for charge, but you can think of it as charge in something. So if something gains electrons, that is reduction. If something gains oxidation state or increases its oxidation state, that is oxidation. So ये दो definitions reduction की तरफ और दो definitions oxidation की तरफ. And the whole idea of redox reactions is to identify what redox reaction is, what is being reduced, what is being oxidized, and how that is happening. Okay, we have already talked about that metals are good at oxidation. So we say that metals oxidize themselves. What do metals do to other things then? Metal, when it reacts with something, it gives electrons to it. So we can say that metal is a reducing agent. So what's a reducing agent? Reducing agent is something that reduces the other thing. Or in other words, it gives electrons, it gives hydrogen. Similarly, we have oxidizing agents, and oxidizing agent is something that oxidizes the other thing. It gives it oxygen, it gives it a higher oxygen state. So metals are good reducing agent. Why? Because metals will give electrons, and that is how they are reducing agent. They reduce the other thing. And non-metals are good oxidizing agent because they are going to gain electrons. So they gain electrons, they oxidize the other thing. Another important reducing agent that you need to remember is potassium iodide, because when you dissolve it in water, it goes from colorless to brown. And why is that? That is because iodide in potassium iodide has a negative charge, but it goes to become I2. And how does that work? It gives electrons away. This thing in water is brown. We have already talked about it in the reaction or in the periodic table chapter, that iodine is brown when you dissolve it in water. And iodide colors, iodide ion has no color because it's not a transition metal ion. So when iodide ion is there, it has a negative charge, but then it loses that and becomes iodine, which doesn't have any charge on it. It is zero, the charge. So it's neutral. You know, molecules are usually neutral, or atoms are neutral. So iodide has lost electrons, so it gives electrons to something and becomes brown in color. So if potassium iodide is there and it reacts and becomes brown, we know that a redox reaction has happened. So we usually use it to check if something is going to react with it. So remember, oxidizing agents react with reducing agents. So metals react with non-metals. Potassium iodide, which is a reducing agent, it will react with an oxidizing agent. If you take potassium iodide and you put it in another reducing agent, it won't react. Why? Because first of all, no reducing agent would try to react with another reducing agent. And secondly, because potassium is too reactive, no other metal will react with that, or usko displace nahi kar sakta. Similarly, on the other side, we have KMnO4. Why are we using potassium? Because they are very strong or very reactive metal. So KMnO4, potassium manganate 7, that's the name, potassium permanganate or potassium manganate 7. This is a purple color thing. Why is it purple? Because you know this manganese in there, that is a transition metal. So purple color comes from the manganese ion that it has. So manganese, in fact, manganate ion, manganese is positive 7. You don't need to remember this, but just remember that the color is purple. And after it reacts, it becomes manganese positive 2, which means that it has gained 5 electrons. This equation isn't something you need to memorize or know about. This is just for your information. So you can see that purple color comes from manganese. The star here means that it's not in your syllabus. Okay. So manganese is plus 7. The charge is positive 7. And then it changes to manganese positive 2, which is colorless. And that is because it gains 5 electrons. Every manganate ion or manganese ion gains 5 electrons. And that means that it has been reduced. So it takes electrons from something. So it can be a little confusing to think about it. So let's revisit them. Potassium iodide is giving electrons. So it is reducing the other thing, which means it is oxidizing itself. Potassium manganate is gaining 5 electrons. So it is oxidizing the other thing. It's taking that thing's electrons away from it. उसके electrons खुद ले लेता है, तो उसका मतलब क्या हुआ? उसने उसको oxidize कर दिया. And it becomes colorless itself. So that is itself, it is reduced, but the other thing is oxidized. So one reducing agent, one oxidizing agent. So if we say that, okay, potassium manganate reacted with something and changed its color, we know right away that the other thing is a reducing agent, because potassium manganate is oxidizing agent. So if it is reacting, the other thing is definitely a reducing agent. Similarly, if you have potassium iodide and it reacts with something, then we know right away that the other thing is oxidizing agent, because potassium iodide is reducing agent. Let's suppose something reacts with both potassium iodide and potassium manganate. Then that means that that thing is both a reducing agent and an oxidizing agent. मतलब जब उसको किसी ऑक्सीडाइजिंग एजेंट से रिएक्ट करवाते हैं तो वो रिड्यूसिंग एजेंट बन जाता है, और जब उसको किसी reducing agent से react करवाते हैं तो वो oxidizing agent बन जाता है. And if something doesn't react with either of them, then that means that that thing is not a reducing or oxidizing agent. So इस तरह हमें चेक करने आसान हो जाता है. Another shortcut that you can use to identify what reaction is redox reaction. So उसको हम कैसे पता चलता है, हम इस definitions को देखते हैं. So for example, here's a reaction. This reaction is combustion. So what's a combustion reaction? Combustion reaction is one in which you react something with oxygen and it burns. So there's a lot of heat there and it's an exothermic reaction. So for example, carbon burning, forming carbon dioxide. Multiple ways of looking at how this is redox reaction. So number one, carbon on the left side has no oxygen with it. Like it hasn't reacted with any oxygen. But carbon on the right side has two oxygen in it. So we can say that this is oxidized. Carbon is oxidized. But there is no way for us to use this definition to figure out what will be a reducing thing. So remember one thing, reduction and oxidation both happen together. ऐसा नहीं हो सकता कि किसी रिएक्शन में ऑक्सीडेशन हो रिडक्शन ना हो. Both of them have to happen together. So sometimes one definition would not be good enough for us to figure out what or how reduction and oxidation both are happening. So here we can say that carbon has been oxidized, but we cannot say what has been reduced. Obviously, we know that oxygen is being reduced, but the definition doesn't tell us that. So we might want to look at another definition. The other definition simply says the charge on an atom or element is zero. That's another one that you have to remember. Now, what is the charge on carbon? Carbon is an atom, right? So carbon's charge is zero. This is called oxidation state analysis. Oxygen is also neutral, so it has a zero charge. Now, think about it like this. If oxygen and carbon reacted in an ionic bond, we know that they did not, but if they did, what will be the charge on oxygen? Now, you know that oxygen is in group 6. So that means oxygen would need 2 electrons more, right, to become 8. So we can say that oxygen would have a charge of -2. If it was ionic. We know it's not, but just for the sake of redox calculation, we are thinking कि अगर ये ionic होता तो क्या होता? So oxygen would have gained 2 electrons because it is in group 6. Okay, what would be the charge on oxygen, the total charge? One oxygen has -2, you have 2 oxygen. So the overall charge will be -4. Acha, to cancel that -4 out, what will be the charge on carbon? +4. Now let's see. Carbon went from 0 to +4. There's an increase, right? So it is oxidized. Oxygen went from 0 to -2. It is reduced, right? Clearly. So we can see that redox has happened. So combustion is one reaction in which it's always redox. Obviously, there's another one, oxidation. Oxidation is you don't need to burn something. It simply oxidizes. So copper, when it reacts with oxygen, it forms copper oxide. Pretty clear that copper has changed from copper element, pink in color, to copper oxide, which is black in color. And how do I know that this has been oxidized? I can use the idea of number one, copper and oxygen react. Copper loses electrons, oxygen gains electrons. So copper losing electrons is oxidation. Oxygen gaining electrons is reduction. So I can clearly see that copper is oxidized, oxygen is reduced. Another way I can look at this is that copper on the left side has no oxygen with it, but copper on the right side has 1 oxygen with it. So copper has gained oxygen. Another way of looking at this is that copper, because it's an element, it has a zero charge, and oxygen, because it's an element, it has a zero charge. But over here, oxygen, if it did react, it would have gotten a -2 charge on it because it's in group 6. So copper would have needed to become +2 to cancel it out. So copper has gone from 0 to +2, so copper is oxidized, and oxygen has gone from 0 to -2, so oxygen is reduced. Another redox reaction that we know of is displacement. Displacement reaction usually occurs when a more reactive thing displaces a less reactive thing. So I'll give you 2 examples of this. So for example, we have copper oxide and it reacted with hydrogen. And this is usually done to purify copper. Okay. So what happens here? Hydrogen is more reactive than copper. So it reacts and forms hydrogen with oxygen. So that's water. And copper is left over. The colors are like this. Copper is black, copper oxide is black, and copper is pink. And because the temperature is high, this is steam, this is gas. Usually it's done like this. You have copper oxide powder here. You push hot hydrogen gas in there. And then you dissolve that thing. So you take that thing and you put it in water. Okay. Or what other thing you can do is that you can simply burn this thing. So instead of dissolving it in water, sometimes you just have a flame here. So this is a flame. And that is because extra hydrogen jo hai, wo burn hoti jaye. So here you have copper oxide. You either have a hot hydrogen gas, but because heating hydrogen directly is very dangerous because hydrogen is expensive, we usually, hydrogen explosive. We usually heat copper oxide. Now hydrogen comes in, reacts with copper oxide. You get pink copper coming out over here because copper is pink in color, and hydrogen simply reacts and extra hydrogen is burned off at the end. Similarly, you can do the same reaction, but for example, when you want to extract iron, so iron is usually reacted. Iron, this thing is called hematite. This is a rock from which we get iron oxide. So this is from hematite. So what we do is we take carbon and carbon reacts with it, and carbon produces carbon dioxide and iron. And let me balance. So you get iron as a liquid out, and this is usually done in blast furnace. Okay, so this is done in blast furnace. We will look at this reaction in more detail later on. So this is done in blast furnace, and what happens here is that carbon is a reducing agent. Again, why? Because carbon is more reactive than iron. Remember the reactivity series. So carbon is displacing iron and forming carbon dioxide. So we can say that carbon has oxidized. Now there are multiple ways of looking at it. On the left side, carbon has no oxygen, but on the right side, carbon has 2 oxygen. So we say that carbon is oxidized. Similarly, on the left side, iron has 3 oxygen, or 2 iron atoms or ions have 3 oxygen. So on the right side, there's no oxygen with iron. So we say that iron has lost oxygen. So this is displacement, or this is redox. Another way of looking at this is that carbon, because it's an element, it has a 0 charge, and iron, because it's an element, it has a 0 charge. But iron oxide, oxygen has a -2 charge and iron has a +3 charge. Why do I know that? Because I did the ratio flip method. So 3 and 2, I flip them, I get 3 and 2 over here. Similarly, in carbon dioxide, we know oxygen was -2, so it was +4. So I can see clearly that carbon went from 0 to +4. So carbon has been oxidized. Iron went from +3 to 0. That means that iron has been reduced. Oxygen did not change at all. Oxygen was -2 on the right side as well as on the left side. So based on all this, I can see that this is a redox reaction. So this is usually done when we are trying to extract iron from hematite. Sometimes we do the same reaction, but we don't have something that is more reactive than the other thing. So for example, if I wanted to get aluminium oxide out, I will have to do a process called electrolysis, because direct redox will be very expensive. So we use electrolysis to make sure that it's easier to do. So displacement is one reaction that we do. We can also do the same thing with, for example, potassium iodide. So potassium iodide, if I were to add chlorine in this, so it has potassium iodide, I know that this is colorless. And I add chlorine, which I know is yellow-green. Again, a color that you need to remember from periodic table chapter. So chlorine, if I were to dissolve in that, what will happen is chlorine is more reactive than iodine. So chlorine will replace it, and iodine brown liquid will be formed dissolved in water. And this is colorless. So based on this, I can easily see that chlorine has replaced iodine or iodide, which means that chlorine is more reactive. And not just that, chlorine is a oxidizing agent. How do I know that? So let me put the charges again. Chlorine as an element is 0. Iodine as an element is 0. Remember, every element or an atom or a compound is 0 overall. Now, potassium is +1. Iodine, because it's in group 7, it will be -1 here. Chlorine is in group 7, it will be -1 here. Potassium is +1 here. So I can clearly see that chlorine went from 0 to -1. So that is a decrease, that's reduction. Iodide went from -1 to 0. So that is clearly an increase. That is, iodine has lost electron. It had a negative charge because it has electrons. It has lost that electron. Now it is iodine 0. That means it is oxidized. There's an increase. And potassium remained potassium as +1 on both sides. Potassium is what we call spectator. Potassium ion is spectator because it did not react at all. No chemical change occurred in it. Chlorine reduced, iodide oxidized, but potassium did not change at all. So this is again displacement reaction. We can use displacement reaction to confirm if something is more reactive than the other. And that is usually done to figure out what is more reactive, what is less reactive, and all that. Okay. So that is the idea of what redox reactions are. Displacement is another redox reaction. Redox reactions are super important in industry because we use it to extract metals. We use them to figure out, we use them to actually make many new things. So redox is important. We also use oxidizers all the time because we need to oxidize other things. Similarly, in many biological processes, oxidants are there and we do not want them. So we have to eat antioxidants to save us from the impact of those oxidizers or oxidizing agents. Okay, so these are oxidizers are basically these chemicals that we need to oxidize other things. Sometimes we don't need them, sometimes we use them. So it has to depend on what we do. Similarly, we have reducing agents. So reducing agents are those things that reduce the other thing. So we also so antioxidants can be called reducing agents. Okay, because so reducing agents, strong metals like sodium, potassium, they're very good reducing agents. Even iron and aluminum are good reducing agents. Similarly, there are reducing agents like potassium iodide that we use when we talk about checking whether something is reducing agent or not. Hydrogen is a good reducing agent. Then there are some catalysts that we use to react with hydrogen and all that. So nickel or platinum, palladium, you will study about them when we talk about environmental chemistry. Okay, so reducing agents and all that. Some other examples of redox reactions are, for example, corrosion, which is also oxidation. So corrosion is another way of looking at oxidation. Corrosion is called rusting if it is happening in iron. So if you had just iron as like this, and it would react with oxygen in the air in presence of water, and it will produce iron oxide. This thing is red in color, which is why jisko hum rust bolte hain. Okay? So iron oxide is rust. You can obviously get that rust from hematite and convert it to pure iron, but it requires some, obviously, first of all, wo cheez kharab ho jayegi. For example, you have an old car, you want to get iron out of it. Obviously, it won't be a car anymore after it goes through that reaction. But rusting will definitely destroy it anyway. So if things rust in presence of water, corrosion happens to iron, we call it rust. So to avoid it, we obviously make sure that iron doesn't react with oxygen. So how do you avoid it? You make sure that iron does not come in contact with oxygen. So hum kya karte hain? We take iron, we paint it. And now there's a barrier. So there was this iron block that I do not want to rust. So I will paint it. So there's a small layer of paint all around this iron block. And now oxygen from the air won't be able to get into contact with. So oxygen won't be able to touch it. Another way I can do this is that instead of having it painted, I can apply a small block of a more reactive metal. So let's suppose I had magnesium. So now oxygen will come and react with magnesium in place of iron because magnesium is more reactive. So I can paint it, or I can add another strong metal there, which is called sacrificial protection. That you sacrifice a more reactive metal to protect a less reactive metal. So this usually happens, for example, we take magnesium blocks on ships. So we take magnesium blocks, we place them on ships because we want to save the ship body from rusting. So magnesium reacts. Similarly, we galvanize things. Galvanization means that you add zinc. So you coat it with zinc. Instead of paint, you apply zinc over there. So zinc will react and iron will not. That's also something that we do. So redox reactions are happening all the time. For example, if you take fruit, that fruit will turn brown after a while. For example, bananas, if you take them, they turn brown and black after a while. That is because there's an enzyme in there that is undergoing a redox reaction. थोड़ी देर बाद वो बहुत soft सा हो जाता है और वो बहुत ज़्यादा black और brown color का हो जाता है. That is oxidation. You take an apple, you let it stay for a while in the air and it will turn brown. Even if it's like if you cut it out open, तो वो अंदर से brown हो जाएगा. Otherwise साइडों से तो definitely skin wrinkle कर जाएगी और वो brown हो जाएगा. And that is all because there's an enzymatic browning. That's the word, but you don't have to remember that. Just remember that it's a redox reaction. Redox reactions allow us to actually live. So respiration is simply a redox reaction. Why? Because what's happening is, so respiration at the cellular level. So you take glucose, so C6H12O6, you react it with oxygen. Obviously, it will release some energy in the process. It's an exothermic reaction. It produces carbon dioxide and water, right? So we balance it using this 666. So this is oxidation. The oxygen in there, obviously you have to use a lot of enzymes and chemicals to actually do this. But this is an exothermic reaction. It's a redox reaction because carbon has been oxidized, hydrogen has been oxidized and all that. So this is a redox reaction, which is respiration. Photosynthesis is a redox reaction because in photosynthesis, what's happening is that you're taking light energy to do the reaction and you're taking carbon dioxide and water and you're producing glucose from it. It is not exactly the opposite of respiration because it happens in a totally different way. There's, I think, Krebs cycle hota hai, and that's very different from what happened in respiration. I'm not sure if Krebs cycle was in respiration or photosynthesis, but there are two completely different methods of how this happens. But the reactions and products are obviously opposite of each other. This is positive delta H. We will talk about this delta H later on. This is exothermic because it needs light energy. And that sunlight obviously allows us, not just sunlight, it also needs enzyme, which is chloroplast, right? So chloroplast is something that they need to do this reaction. So you need not just light energy, but also catalyst to do this reaction. There are many, many other biological processes that use this. So the way we get energy in the muscles and everything, ATPs, they react with I think they reacted with NADPH or NADH or those kind of things. They're all just redox reactions happening in our body. So redox reactions happen in soil as well when plants are growing up and all that. Redox reactions are all around us. So just to give you an idea of where redox reactions apply, redox reactions apply in respiration. The redox reactions apply in electrolysis. Redox reactions apply when you're generating electricity. Redox reactions apply in hydrogenation when we make margarine. Redox reactions apply in volcanic activity in sulfur. So there are many, many applications of redox reactions, but you can identify all of them based on these four things, the definitions, that if something loses electrons or hydrogen, then that is oxidation. If something gains oxygen or oxygen state, that is oxidation. And you can do either the electron transfer to figure out if this is oxidation or reduction. You can see that, all right, a metal will lose electron, a non-metal will gain electron, that's electron transfer. So you can easily see that, all right, this is reduced or this is oxidized. You can also do the oxygen state analysis, and oxygen state analysis requires that you see the charge on an atom or an element or a compound is zero. And then you figure out what would be the charge if this thing was reacting as in an ionic reaction. So that is also how you know whether it's a redox reaction or not. So apply the definition or the oxidation state analysis or the electron transfer, and you can easily figure out whether something is a redox reaction or not. Some applications: combustion, oxidation, displacement, respiration, photosynthesis. These are some applications of redox reactions. And that's it.